The bedrock of almost every database is a simple hash map. You store a unique key, and you associate it with an opaque value. Because this operates entirely in memory, data retrieval is nearly instantaneous. But memory is bound by strict physical limits and fractures. To build a production-grade system, we're going to engineer a distributed key-value store, designed to handle 10 million daily active users and roughly 4 terabytes of raw, persistent data. The service-level objectives are unforgiving. Whether handling user session data or an e-commerce shopping cart, during a massive traffic spike, it must return reads and writes in single-digit milliseconds. A single server running an in-memory hash table gives us the mathematically fastest access possible, big O of 1. But a single machine cannot physically hold 4 terabytes of RAM, and if the power supply fails, every piece of user data vanishes instantly. To survive the capacity constraints and the certainty of hardware failure, we must distribute the state of the database across a network of multiple physical machines. Slicing data across a network solves the volume problem, but the moment you introduce a network, you introduce the most dangerous tension in distributed systems engineering, the CAP theorem. To distribute the data, we first have to figure out how to partition it. We need a routing layer that dictates exactly which server in our cluster holds which specific key-value pair. The standard approach is modulo hashing. We hash the key and divide it by the number of servers. But watch this horizontal array of servers. If one machine goes offline, the denominator changes. The math breaks. Every incoming data packet instantly misaligns, forcing the network to migrate massive amounts of data just to the store order. We eliminate this data reshuffling by implementing consistent hashing. In this model, we map both the physical servers and the incoming data keys onto a conceptual circular hash ring. When a data packet hashes to a specific coordinate, it simply moves clockwise around the ring until it hits the first available server node. By utilizing this circular geometry, the crash of a single server no longer scrambles the whole network. The data mapped to the failed node simply continues moving clockwise and parks on the next adjacent machine. Only a fraction of the keys migrate. To prevent uneven data distribution, where one node takes all the traffic, we implement virtual nodes. We map multiple smaller coordinates on the ring to a single high-capacity physical server off the ring. Virtual nodes completely decouple logical partitions from physical hardware. We can assign more virtual nodes to powerful machines, balancing the load perfectly and enabling the cluster to scale elastically as traffic grows. In a global data center, hardware failure is not a possibility, it is a mathematical certainty. Disks corrupt, motherboards fry, and network cables get severed. High availability requires us to asynchronously replicate our data across a configurable number of servers, which we call N. When a network connection breaks between these replicas, architects are forced to choose. The system can either pause operations to ensure strong consistency, or it can keep accepting reads and writes to maintain high availability, accepting that some users might briefly see outdated information. We tune this exact trade-off using quorum consensus. Here we have a coordinator node routing requests to 3 replica servers, governed by the formula W plus R must be greater than N. N is the total number of replicas, W is the write quorum, and R is the read quorum. If we configure W to 2, the coordinator only needs 2 successful acknowledgements to confirm the write and move on. Configuring the formula so that W plus R is strictly greater than N guarantees strong consistency. It mathematically forces at least one node to overlap between the write group and the read group, ensuring the system always retrieves the most up-to-date data. But for a massive, write-heavy consumer system like a global shopping cart, we intentionally break this formula. We set the parameters lower to prioritize high availability, adopting eventual consistency to guarantee the database never goes offline, even during severe network partitions.
Eventual consistency keeps the system fast, but it creates a dangerous byproduct. If 2 users update the exact same key simultaneously on different disconnected nodes, we instantly generate conflicting versions of reality. Relying on system timestamps to determine a last write wins scenario is heavily flawed. Server clocks drift across physical data centers, meaning the timestamp on a piece of data might not reflect its actual chronological order. We resolve this deterministically using vector clocks. Look at these two isolated nodes modifying the same data block. Instead of relying on time, we attach an array of server and version counters directly to the data item, tracking its exact causal history step by step. By comparing the version counters, the system can mathematically prove if one update is a direct ancestor of another and can be safely overwritten. If the counters reveal a branching path, the system detects a sibling conflict. Vector clocks shift the burden of resolving concurrent conflicts out of the database and back to the client application. The client merges the data, like combining two items in a shopping cart, guaranteeing that a network error never silently deletes user data. Now we shift from the macro network down to the internal mechanics of a single physical node. Standard relational databases rely on B-trees for storage. Under extreme write-heavy workloads, B-trees suffer severe latency. They rely on random disk I/O, mechanically forcing hard drives to physically seek disparate blocks of data. To achieve single-digit millisecond writes, we abandon B-trees and deploy a log-structured merge tree, or LSM tree. This visual represents the first step of an LSM write. Incoming data bypasses the disk entirely, dropping rapidly and sequentially into an in-memory grid called a memtable. To ensure that data survives a sudden power loss, the exact same payload is simultaneously appended to a write-ahead log directly on the disk. Once the in-memory memtable reaches its size limit, the entire structure flushes down to the disk, freezing into an immutable file called a sorted string table, or SS table. By appending data into memory and flushing it in large, sorted batches, LSM trees convert slow, random disk writes into lightning-fast sequential operations. But LSM trees introduce a severe trade-off. Because SS tables on the disk are immutable, a single key's update history is scattered across multiple different files. A read request is forced to comb through several fragmented blocks on the hard drive to find the correct data. In a read-heavy environment, this fragmentation causes unacceptable latency spikes. To fix this, we implement Bloom filters. A Bloom filter is a highly compact, probabilistic data structure. When a read request enters the node, it hits this filter grid first. The grid flashes red, definitively proving that the key is not in this specific file, bouncing the request away before the disk ever has to spin. By shielding the disk from useless searches, Bloom filters neutralize the inherent fragmentation of the LSM architecture, ensuring read latency stays in the single-digit milliseconds. Let's trace a client request through the fully assembled architecture. The data hits a load balancer and enters the system, routed flawlessly using the consistent hash ring. This bypasses the physical constraints of any single machine without risking catastrophic data reshuffles. The coordinator node then replicates the data across the cluster using quorum consensus, while vector clocks track the precise history of the data, neutralizing hardware unreliability and network partitions. Inside the target node, the write hits the memtable, while Bloom filters guard the fragmented SS tables against useless disk reads, completely circumventing mechanical speed limits. This interlocking sequence of algorithms forms the backbone of highly available, production-grade systems like DynamoDB and Cassandra. System design at this scale is rarely about finding a flawless piece of hardware. It's about layering strict mathematical abstractions to systematically defeat physical bottlenecks.